Yeah, good morning, my dear students. Today I am going to discuss the principle of atomic absorption spectrometry. What is atomic absorption spectrometry? The atomic absorption spectrometry, it is just like your UV spectroscopy where molecules are condensed there. Here we are concerned with atoms. So when we are talking about the atoms, the principle is basically in case of molecules there is a rotation followed by vibration followed by electronic excitation. But in case of atomic spectrometry, in case of atoms, there is no rotation, no vibration. Directly the electronic transition will be moving from one state to another state. So that is the basic principle of atomic spectrometry. So when we are talking about the principle, the major principle is the samples are vaporized at a higher temperature, say 2000 to 6000 Kelvin, and the concentration of the atoms are determined by measuring the absorption or emission of characteristic wavelength. Right? So this is a very important principle of atomic absorption spectrometry. When we talk about this thing, most of the time the samples are vaporized at a higher temperature, say 2000 to 6000 Kelvin, right? And the concentration of atoms can be measured either by absorption or emission of characteristic specific wavelength. If there is an absorption of characteristic wavelength, then it is called atomic absorption spectrometry. If it is an emission, it is called atomic emission spectroscopy, right? So basically why we call it as atomic absorption spectrometry? Spectrometry means this is mainly applicable for quantitative analysis. This technique is applicable mainly for quantitative analysis. It is not very limited to qualitative analysis. That is one of the disadvantage of the technique, where we can find out very little information of the chemical nature of the sample, right? So this is all about the disadvantage of the atomic absorption spectrometry, right? So what is an advantage? What are all the various advantages of atomic absorption spectrometry? When we look at that, how this absorption of discrete wavelength of light by the ground state gas phase free atoms. So in atomic absorption spectrometry, there is an absorption of discrete wavelength of light by the ground state gas phase free atoms. So the major contribution here is atoms are not directly moving from one state to another state immediately, right? So they must be present in the gas phase ground state. Then only the atoms will be going for electronic excitation. This is the most fundamental criteria. So if any atoms are there in the form of solid or liquid, those atoms has to be converted into the gas form. Then only they will be present in the ground state. Then they will be excited to the excited state, right? So in order to bring the atoms into the gas phase ground state, we need the help of an important component called atomizer. Right? If you want to bring the elements, or if you want to bring the atoms from the ground state, especially in the ground state in the gas phase, you need the help of an atomizer, right? So that is the very important aspect. So what is an advantage of this atomic absorption spectrometry? Most of the elemental analysis, they will provide the quantitative information of around 70 elements. The second advantage is it is routinely used technique to determine the parts per billion and parts per million concentration of most of the metals. The third advantage, when the given element can be determined in the presence of other element which do not interfere by absorption of sample wavelength. So this is also one of the important technique, right? You no need to separate any elements by keeping that element along with the same element, right? Suppose if you want to identify the sodium chloride, sodium present in the seawater. You have chloride, manganese, many other elements are there. You no need to separate them. Directly we can perform the atomic absorption spectrometry to find out the concentration of sodium ion. Right? So this is an advantage of the technique, right? That the only disadvantage, as I already told, there will be a limited information on the qualitative aspect. That means we can find out the concentration of sodium in the seawater, but we may not know what is the chemical nature of sodium. Whether the sodium is present in the form of sodium carbonate or sodium bisulfate, that we cannot able to identify. So this is the limitation of atomic absorption spectrometry. That is the reason we give us spectrometry. So there only one technique will be carried out in a very efficient manner, that is quantitative analysis, right? Now when we talk about this atomic absorption spectrometry, I am just providing the general layout of this atomic absorption spectrometry. So we have the light source. The light source is connected with the light source. Basically there are two type of light source we are using in atomic absorption spectrometer. One is the hollow cathode lamp. Another one is the electrode-less discharge lamp, right? So most of the time we are using, for every individual element we are using individual hollow cathode lamp, and for certain elements where they are present in the form of volatile elements are there we are using only the electrode-less discharge lamp. Example like arsenic, germanium, selenium, like volatile elements are present. In those cases we will have the electrode-less discharge lamp. From the light source, we will be going to the atomizer compartment. The atomizer is very, very important. Why we are using atomizer? To make any sample into the gas phase ground state. Then only the atom will be going to the excited state. The major condition is the atom should be present at the gas phase ground state, free atom. Then only they will go for excitation. So to make the atoms in the gas phase ground state, we need a component called atomizer. For this atomizer, we need a sample. The sample will be a solid sample or liquid sample. The sample can be sucked in, and this atomizer compartment, all the things will be taking place. We will discuss the mechanism. And this atomizer is attached with fuel and oxidant. This is also very, very important. Without fuel and oxidant, the atomizer will not work and they will not convert the atoms into gas phase ground state, right? So once the gas phase ground state atoms are coming here, so these gas phase ground state atoms, for example, if this is the gas phase ground state atoms, so they will be getting excited. The gas phase ground state atom will be going for excitation, right? And they will be there in the flame as such, right? And whatever I told already, there is an absorption of characteristic wavelength in the flame. So that will be captured by the monochromator, which will isolate the separated lines. And monochromator is attached with the detector. Basically, the detector used is a photomultiplier tube, or sometimes we are using charge coupled devices or photodiode array detector, right? And it is connected with amplifier and finally connected with readout device, right? Now, basically, when we talk about the fuel oxidant mixture, there are different types of fuel and oxidant we are using. Some of the examples I have given here. Acetylene air is the most commonly used fuel oxidant mixture at a temperature of 2400 to 2700 Kelvin. We can also use acetylene nitrous oxide at a temperature of 2900 to 3100 Kelvin. We can also use the fuel oxidant as acetylene with oxygen at 300 to 3400 Kelvin. At a higher temperature we are using. Sometimes if you go for a very high temperature, we can go for cyanogen oxygen flame, where we are using for calcium atoms, right? So this is at 4800 Kelvin we are using this cyanogen oxygen flame. Now coming to these atomizers, what type of atomizers are basically using in atomic absorption spectrometer? The first important type is flame atomizer, which is the most conventional one is flame atomizer. In the olden days they have used, and the example for flame atomizer is premix burner system or nebulizer burner system. The second important atomizer is electrothermal atomizer, ETA, and the example for electrothermal atomizer is graphite furnace. Most of the modern atomic absorption spectrometer uses this graphite furnace. The third important atomizer what we are using is cold vapor atomizer, CFAAS. The cold vapor atomizer is used for elements like mercury, right? And we can also use hydride generation atomizers for atomic absorption spectrometry, especially whichever substances or elements are forming the volatile hydrides, right? For example, selenium, bismuth, or germanium, arsenic, these type of elements, if you want to analyze them, so automatically we can use this hydride generation atomizer. And sometimes we are using glow discharge atomizer, especially for the solid metal samples. If you want to analyze the solid metal samples, we can use the glow discharge atomizer. So these are all the various atomizer components used in the atomic absorption spectrometry, particularly to make the sample into the gas phase ground state free atom. That is the major purpose, right? Now, what is the mechanism of this atomization? How this atomization? That means I told already how the sample will be getting excited. What is the basic fundamental mechanism behind this flame atomization, right? So I am just giving an example here. I am taking the metal cation, any metal cation I am taking. I mix it with anion that is present in the beaker as a sample. So the sample will be in the solution form. So what will happen? The first step it will takes place is nebulization. The first important step is nebulization. So nebulization means converting the solution into a fine mist of aerosol droplets, which we call it as aerosol, right? Aerosol will be converted here. So all the metal cation and the anion will be converted into form of aerosol. So that is the first step called nebulization. The second step taking place is desolvation. This is the second important step called desolvation. Desolvation means any solvents present in the sample will be removed here. So what will happen? The aerosol is a mist of droplets. So there we are removing the solvent, so that becomes a solid, right? So once we do the desolvation, it becomes solid. So M plus A minus gives Ma, right? Ma is a solid as such, right? That is the second step. And the third important step is liquefaction. Now we got the solid, we are converting them into liquid form, right? So when we do the liquid form, then Ma will be converted into same Ma where liquefaction takes place. The solid will be converted into liquid. And the fourth step is vaporization. This is also very important step. Most of the sample, liquid sample has to be converted into vapor form, right? So the fourth step, Ma will be again converted into Ma by the step called vaporization. So vaporization is nothing but the gas form you will be getting. The fifth step is atomization. This is very, very important step. Atomization. What is the purpose of atomization? To make the atoms in the gas phase ground state, right? So the fifth step, atomization, what will happen? The Ma will be converted into M dot plus A dot. M dot is basically called as free metal atoms. Free metal atoms in the gas phase, right? So that is the purpose of atomization. And after atomization, then the sixth step is immediately going for excitation. So excitation means moving from ground state to excited state. As same like your electronic transition in UV. So this M dot plus A dot undergoing excitation, you will be getting M star, right? And the last step, seventh step is ionization. So ionization is not taking place normally. So this excited metal atom, that is metal atom when it is getting excited. So some of the metal atoms will go for ionization, provided they should have the low ionization energy and high temperature. Particularly if you are using the atomizer with a very high temperature, like plasmas if you are using, and as well as if you have the metals like alkaline earth metals like sodium, potassium, they have the low ionization potential. So only for those elements, the atoms after excitation, they will go for ionization also. Otherwise, normally it will not be converted into ions, right? So that is the basic mechanism of flame atomization, especially for atomic absorption spectrometry. But for atomic emission, there is only one step taking place extra. So the excited atoms will be again coming back to the ground state, right? Where there is an emission of radiation of specific wavelength, that is called atomic emission spectrometry. Okay, the excited atoms will be again converted back to ground state with the emission of light radiations of specific wavelength. So that is the only extra step in atomic emission spectrometry, right? Now, as concerned with this thing, this also the basic principle is concerned for atoms also Beer-Lambert's law with some slight modifications. What is that modification? A is equal to ABC, Beer-Lambert's law. Here, the small a is nothing but absorptivity of the sample. So, absorptivity is equal to constant into F. What is this F? F is called oscillator strength, right? And if you look at that B is the path length of the sample. That is path length of the flame. So this is the B. The term is called B. This is called B. B is the path length of the flame, the width of the flame. Normally it is 5 centimeter. Some cases the width of the flame will be 10 centimeter, right? And concerned with the C, what is called C? C is the concentration of the ground state atoms in the light path. What is the concentration of ground state atoms present in the light path? That is called as C, right? So that is why it is concerned with the Beer-Lambert's law. Is it clear? So therefore any atoms, there is no rotation, there is no vibration, directly there is an electronic transition from ground state to excited state, provided the atoms should be present in the gas phase ground state as such. You have to bring the atoms into the gas phase ground state, then only the atoms will get excited easily, right? So this is all about the principle and the general layout behind atomic absorption spectrometry. I hope it is clear for you. So thank you, my dear students. Thank you very much.